Hi, my name is Rika. I am a PhD student at the Robotics Perception and Learning Division at KTH in Stockholm. And this is a talk for Liam Paul and his group at University of Montreal and people from Mila who are joining us as well, or who were joining us as well on the original call when I had this presentation. Unfortunately, then my laptop was not functioning well, so I couldn't show properly the videos of the robotics hardware experiments. So I'm re-recording this talk on my own here, and I will try to address a bit more in depth the points for which people had questions during the talk. All right, so the talk is about transfer-aware kernels, priors, and latent spaces from sim to real. We will start by looking at how to build kernels that help achieve ultra-data efficient Bayesian optimization to optimize robot controllers. And then I will talk about how to interpret simulators as regularizers and achieve better performance with variational inference methods. And then I will introduce the idea of building modular latent spaces. So overall motivation is that online optimization of robot controllers is difficult. It's because we need to adapt to new environment with very few trials or episodes, and we would like to minimize undesirable impacts of exploration on the environment and the robot. So my goal is to build transfer-aware representations that help sim to real, even if they are constructed from imprecise simulations. First, we'll consider optimizing parametric controllers. So our problem is to find an optimal controller with parameters x star, such that we're optimizing a certain objective function f, or this could be cost, and then we will be minimizing it. We will model the posterior mean and uncertainty over f with a Gaussian process, with the mean function and the kernel. The prior mean function is usually taken as an informed zero, and then the kernel is one of the key objects here. It determines how much the influence of the already sampled points extends in the search space. So here is a quick visualization of Bayesian optimization. The acquisition function denoted here in green will dictate where we would sample next, and we would reduce uncertainty globally across the space, but only enough to find promising regions for us. And then we would sample more points in the promising regions, leaving other regions that are not likely to perform much better than what we have so far, leaving those underexplored. All right, but the limitation here is that most kernels are stationary, so they do not embed additional knowledge about the search space. They rely only on the differences between controller parameters, and this usually computed as a Euclidean distance. Now, we would learn kernel transforms from simulation, and this will help us remove stationarity, and we will also show how to reduce exploration in undesirable regions. So in the previous work, there has been this concept introduced called behavior-based kernels. And intuitively, this makes sense. Instead of looking at the Euclidean distance between controller parameters, we would like to characterize each controller by the probability distribution over the trajectories that it induces. So what are these trajectories? Well, if you have a walking robot, that maybe we're looking at the center of mass of the robot and the positions and velocities of the links of the robot, and the trajectory is basically the trajectory in the configuration space of the robot that they traverse. All right, so this behavior-based kernel introduced in by Wilson et al. In 2010 said that we will build a kernel by exponentiating the negative of the symmetrized KL, where symmetrized KL is obtained here like so from the usual definition of KL divergence between two distributions. We will take inspiration from BBK, but we'll show that it does not scale to high dimensional domains and controllers. So our approach would be to enable measuring controller similarity via distributions of the latent paths that they induce. So we will simulate a large number of controllers, then collect their trajectories, and we will build the latent representations of these trajectories. So here is a sequential variational autoencoder that we define. The x here is the controller parameters, xi's are original trajectories, and tau's are the latent paths whose embedding we would like to learn. So using the variational inference and structuring this in a particular way such that we would establish correspondence between the controller parameters and the distribution of the latent path, we would learn the corresponding notions. So probability of trajectories in the original space that are induced by a certain controller, and the probability of the latent paths that are induced by this given controller. For best practical results, we will use L1 norm of the difference between the latent means as the proxy to KL in the setting. We'll show the correspondence in our write-up for this. And in this way, we'll obtain the kernel that is based on this sequential variational autoencoder. And now this will be a kernel informed by simulation. We also let the user specify region that is undesirable for the robot to visit. So a region in the space of trajectory. So for example, if this is a walking robot, it's very easy to figure out if the robot is falling based on the location of the center of mass, like how high it is above the ground and maybe its velocity. And so then the users can say that the trajectories that correspond to the robot falling are undesirable. And with this, we can see what fraction of time each trajectory in the original space spends in the undesirable regions, and we can learn the analogous notion, this C here, the analogous notion of this in the latent space. So then we will achieve a dynamic compression by scaling our latent means by 1 minus this expectation of how undesirable the trajectory is, and this would give us the result that the representations of undesirable trajectories are scaled down and represent a smaller portion of our search space, and hence we would spend less time paying attention to controllers in this region when we're running Bayesian optimization now in a latent space on hardware. And so during BO, we can quickly estimate all of the quantities that we need for this. So the latent means, the expectations for how undesirable the trajectory is from the latent encoding. So we will not need to look at these higher dimensional representations here. Higher dimensional in this case, meaning that, let's say, if we sample for 10 seconds at 1 kilohertz, all the positions and velocities of all the joint of the robot and maybe the objects that we're manipulating with, if it's a manipulator, then this would be kind of a fairly large amount of data, whereas here the latent paths can be, 10D or something like this, small. All right, so the good part about this setup is it has been designed in such a way that all the latent components here, so this, the probability distribution of the latent paths and their undesirability, all of that can be adjusted during BO automatically. And this is in contrast to some other approaches like deep kernel learning or manifold GPs, which would need to adjust all of the kind of larger neural networks that have to do with the overall space. So this is how we achieve the modularity, and we are even able to handle the situations where the simulation does not reflect very closely the reality. And so we will need to adjust, how the embedded representations, how do they correspond to the controllers that are actually now showing us the behavior on hardware. All right, so let's take a look at the hardware results. So this is a stable pushing task where the human robot's objective is to push 2 paper towels to the middle of the table without tipping them over. So you can see here that there are a few random trajectories sampled at the beginning, and very quickly we're able to identify the behavior that is reasonable. And then with only a few more trials, so here overall we would run 10 trials, we would be able to push these 2 paper towels jointly across to the middle fairly well without tipping them over. And we show that we improve over the baseline BO with squared exponential kernel, and of course also over the random search. All right, but the most interesting part is that we can also run exactly the same architecture. So train and SVIE with exactly the same parameters on simulations that are coming from this DAISY Hexapod robot. And likewise, we would learn the embedding of the trajectories map, but now here for the positions and velocities of the joints of this robot. And within, again, 10 trials, we would be able to reliably find gates that let us proceed forward. So some of these would be, semi-crawling gates like this. So this is some progress, and according to the objective of moving forward, this is okay. This is pretty stable, but we will also show that we would be able to stand up and walk if this is a more desirable behavior. So I think this is coming up next, right? And you can find it surprising that, okay, by the 5th trial, and we've done, 2 initial trials at random at the beginning, but the 5th trial, we're already able to do that. So this is coming from the fact that, right, the controllers that we're exploring would be very far from the few initial ones that have fallen, right? And so this basically, lets us go into the furthest away space. And since the space is informed by simulation, this furthest away part of the space is likely to contain the controllers that are not like the falling ones, so the ones that are walking. All right. So another thing is that we can show that the controllers that we found on this environment with the carpet, the best performing controllers we take now and we run them on a different surface. And we can see that, you see the crawling one, it can still make the progress forward. The squared exponential one is on the right, and our approach here is on the left with the sequential variational autoencoder in the kernel. And we also transfer the behavior where we had a walking controller, so that stands up. And this is nice because, you know, the friction properties of the surface is very different. So at least we can show that, okay, these controllers are somehow useful in different environments. Okay, so we in simulation also investigated the effects of changing various learning parameters. People usually ask, okay, do you need low dimensionality? And we say that, right, we can compress the space and make this latent path like nine-dimensional, but we can also make them 30-dimensional, and we don't lose too much of the performance, especially if the user specifies kind of what part of the trajectories are undesirable, like, you know, the falling, you know, they don't want the robot to fall. And we've used other kernels other than square exponential to compare kind of how the performance ends up being if there are other ways to specify the kernel. Okay. We would also like to be able to handle extremely low fidelity or faulty simulations, like when our simulation, for example, does not have enough information to capture the correct physics phenomenon. We could try to recover from these severe faults by adapting the kernels online, but that might be too slow with these extreme cases. So in this case, we might have negative transfer, but to guard from negative transfer, we would have this approach where we define a probability distribution over kernels, and at each BO trial, we randomize the choice of whether uninformed or informed kernel that is based on simulation is used. And with this, we call this Bayesian optimization with Bernoulli alternation kernel, BO-BAK. This approach is robust to negative transfer in practice, and it is also simple to analyze theoretically. So this definition here is not sophisticated, but it is on purpose, because, for example, if we say we take a constant percentage of the time that we sample from the uninformed kernel, then in theory, this approach should be no worse than the usual BO with half of the budget of trials, and we can actually obtain all of the original consistency and regret bounds guarantees that we would get for BO. And in contrast to other common formulations, like, for example, taking the weighted combination of kernels, summing them, or doing some other arithmetic on the kernel, they actually complicate the theoretical analysis quite a bit, and they're also, we've shown, vulnerable to negative transfer. So here is an example of how this would work on BO on the real robot. So together with my colleague here, we have defined a way to extract the high-dimensional input from a depth camera. And then my colleague Mia, she trained a convolutional neural net to extract from OpenRave simulator task stability scores and also grasp suitability. So this is task-oriented grasping, where we want to grasp, let's say, on a certain part of the object that is appropriate for the task. All right, and then I run Bayesian optimization on hardware to find the task-appropriate grasps and improve them in a few trials. So for example, here, the grasps suggested by simulation were either unreachable or really awkward for the robot, and then with the Bayesian optimization, we found the better approaches. And here, we can also show that with Bayesian optimization, we sample a wide range of controllers. So that lets us do the exploration, but also once we find successful approaches to grasping, we can improve them further to achieve a more stable grasp. So we'll take a look at an example. So this is the best grasp suggested in simulation, and this does not succeed here because the cup is moving. The task here is to hand over, so it's not necessarily beneficial to grasp on the handle, so we can grasp from the top, for example, and this is Bayesian optimization suggested this approach, and this has now succeeded, so the user can get the cup. And here are a few trials with the spatula. So here again, the few grasps suggested by simulation were not successful. A few ones based on BO are not successful, for example, here, where the desired grasping approach is out of reach for the robot. It's out of the workspace. And then the BO tries to find a grasp that is on a different part of the object and finally succeeds in getting the robot in configuration that is appropriate for the grasp, and the grasp succeeds. All right, so overall, what we would like to do is to show that if we have grasps for the objects that were really hard to model in simulation, and the top grasps that we could suggest from, sifting through a bunch of the simulated ones, they fail, with BO, we can recover from that failure very quickly, right? So this is the performance of, mean best score here being, whether the grasp was successful and stable. But moreover, what we can do also is we can recover from the negative transfer that is more severe. So here, this is just showing this blue curve where on the further runs, we are able to use the simulation-based kernel with this Bernoulli alternation kernel approach and improve the success rate of grasping, task-oriented the grasping by quite a bit. But now we will actually, on purpose, degrade this kernel even further, such that it has, depending on the object, from 30 to 100% to top 25 error rate, meaning basically the most of the information that is embedded in the kernel is useless. And with this is the black line when we're using BO-BAK with this degraded kernel. And we can see that initially, as expected, we have the negative transfer. Performance was worse than the BO baseline. But then after a few initial trials, we're able to outperform this and even leverage the remaining kind of like little information that remains about what is useful from that simulation. We're still able to leverage that and perform better than the baseline. Now let's step outside of this trajectory-centric view of Bayesian optimization and think of other ways that general purpose simulators can be used for sim-to-real. So they can be a valuable data source for flexible learning approaches like, for example, model-free reinforcement learning, but training policies in simulation and then directly applying them to hardware can result in very brittle policies if there is any mismatch between simulation and hardware real-world conditions. So here we'll look at the new way to use black box simulators as regularizers. So we propose to regularize the decoder of a variational autoencoder to simulation with the latent space bound to a subset of simulator parameters. We, in this work that was just presented at ICRA, show the ability to learn parameter posteriors that match the real world using a small number of hardware trajectories. So here I'll describe our approach that would help us convert a deterministic simulator with some default set of parameters to a stochastic simulator with a probability distribution over these parameters that matches the real world. So we initialize the parameters with some uninformed way with some default distribution at the beginning. And then we use either a random policy or a policy trained with RL on this initial uninformed distribution to collect a set of real trajectories. And then for now, we set these real trajectories aside and we collect a lot of simulated trajectories and then pre-train the decoder to output what we would expect the simulator to output. So the input to the encoder here is going to be the current state and the simulation parameters, so sampled from this latent space of the VIE, and the decoder will be aligned to output what we would expect a simulator to output. And then we recall that we had the set of real trajectories, and we continue training here with the evidence lower bound objective, just like we usually do training for the autoencoders. But training the encoder to encode the real trajectories and decoder to decode these real trajectories. And then this lets us update with this standard training procedure. This lets us update the latent space, which now reflects the shifted probability distribution over the simulation parameters that better reflects better aligns with the hardware trajectories that we've used. And then we continue. So here we update our posterior probability distribution. This can be a mixture. And then if we're training RL here, we can update the RL policy now and get the new set of hardware trajectories. Okay, so with this, first we conducted a number of simulation experiments, so like sim-to-sim. And here one prominent example that we had, so we compare the quality of the predictions that we get because our decoder can be basically viewed as a forward model. So it takes takes the current state and action and produces kind of as the output the coding of the next state. And we can show that with this dead-to-stock algorithm, we can obtain better predictions with 10 kind of surrogate real trajectories. Now we're still doing just in, but like the version of the simulator whose parameters we've hidden from the algorithm, and we consider kind of the surrogate reality. So we can just take 10 of them, and we would achieve better test log likelihood on these reconstructions than a conditional variational autoencoder would achieve with 1,000 of these trajectories, so 100 times more data. So that's very promising, and with that we were ready to take it to the hardware experiment. So here our hardware setup is a ABB YuMi robot, dual arm, and we're going to be doing the object tracking with Kinect and SimTrack. Our object is going to be this cheese box from the YCB data set, but here we will have an advanced kind of version of the pushing and reorienting task, where we would place at an unknown location a weight within this box, a heavy weight. And so now when we are going to push this box, the point would be to identify the center of mass of it and the friction. And those would be the simulator parameters, and the overall task would be to reorient the box to the desired position on the table. Right, so we would we set up the task in order to be able to explore potential for a large sim-to-real mismatch and how this algorithm that we're proposing can help us with it. And to illustrate the challenges of this task and contrast it with the usual kind of pushing tasks, I should say that here we do not assume the uniform distribution of the center of mass, because this box is placed in an unknown location. This task is not planar because the robot can lift the box up. You will see it in the experiments as it's pushing it. We introduced a high friction condition where we place a high friction pad underneath the box, and that can have kind of unpredictable behavior like rapid flipping of the box to the other side. And our scenario can also accommodate a wide range of policies, like pushing with one hand or pushing with one arm, or pushing with two arms. Okay. So here, as I was saying before, we can collect a set of real trajectories. Now here we've trained proximal policy optimization reinforcement learning algorithm initially on an uninformed set of just default set of parameters that are not aligned to reality. And then with this, we run the dead-to-stock algorithm, and we look at the posterior distribution over the center of mass that we obtained from the latent space. And we can see that only after 2 iterations, we are kind of shifting in the right direction. So the center of mass here is on the left. And you can see that from an uniform distribution, we have this shift. And the friction is also roughly matching, kind of like the mode of the friction is roughly matching our real world estimates for the friction that we've done with an inclined plane test. And we can show that after further iterations, we can also obtain these estimates for the more challenging high friction condition. Here, you know, the center of mass of the box is on the other side, and we can infer it. So we can see how the center of mass is different. And also we can see that the friction is indeed here estimated as an increased friction. Right, so that in the last set of experiments, we would want to see how this benefits for something like fine-tuning RL policies. So first we train RL, this PPO RL, and picked the best performing policy that was working for the low friction condition. So that's kind of success of RL. And then we saw what this policy would do when we placed a high friction pad underneath the box. And of course, the performance of that was very bad because there is a pretty big mismatch between the low friction and high friction condition. So then we fine-tuned the policy with dead-to-stock, meaning that we have estimated the posterior of the simulation parameters and then trained the fine-tuned the PPO policy using this better aligned posterior. So let's take a look at what happened here with the hardware experiments. Actually, let me speed this up further. So this is the box. We're aligning it to be, standing parallel to the edges of the table and in the center. And you can see that in the low friction condition, this was successful, easy task. Now this is the high friction condition with the pad underneath, and the center of mass of the box is on the left. So you can see that there is this wrapping flipping behavior that is not expected in the low friction condition. So when we fine tune with dead-to-stock, then you can see here that the actions are a lot more careful, and the policy is able to push the box at a little bit lower point in order to prevent the rapid flips. So that's a success for this fine-tuning result. And now we will consider what are the interesting things that we can do with the structure of the latent spaces. So we'll consider the problem of learning latent state representations from high-dimensional streaming observations like RGB images. And we know that unsupervised learning approaches like VIEs, they can have promising results, but they lack data efficiency to be able to learn from hardware, especially in non-stationary settings like when we're at the same time learning an RL policy. So previous work proposed using domain knowledge to structure the latent space. Like, for example, the simplest example of this is something like imposing the continuity between the consecutive latent states. And there are other ways of structuring this, but many of these approaches are heuristic in the sense that they impart some prior knowledge, but the comprehensive set of such heuristic would be pretty tedious to manually incorporate. And so we would like to take a broader perspective on this. And we want to learn a set of relations that are approximately independent. And in this work, we will define independence rigorously. So this is our new work that has just come out on arXiv. And this is in collaboration with MSR Cambridge that I was visiting last winter, and then we continued collaboration to finish this work. So we will, I'll just give a brief set of definitions that are necessary to follow the basics here. So we say that Rn will be our ambient space of all possible latent state sequences that are defined by tau. And we would let M be a submanifold of the actual state sequences that our dynamical system can generate under any control policy. And then the submanifold can be specified by describing all equations, aka relations, that have to hold for points in the submanifold. Right? So in linear algebra, there is a notion of dependency as a dependency of a linear combination of vectors with constant coefficients. We're familiar with that, right? But in our nonlinear setting, the analogous notion is that of syzygy. And so a collection of functions, now we have functional coefficients here instead of constants. The collection of functions is called the syzygy if when we multiply these functional coefficients by our relations G, then and then sum them up, then the sum is 0. So we have a relation between these. But this direct translation from the linear to the nonlinear case yields the definition that is not very useful because it deems every pair G1 and G2 dependent, as you see here. Because basically f is a function, but it can also be viewed as a relation. So this is the problem here. So we define a restricted syzygy where we are also saying that we will have functional coefficients f1 through fk minus 1. And then kth coefficient we fix to a constant. And this results in us being able to define a restricted independence, which is analogous to using the original syzygies, but now we're using restricted syzygies here with this last functional coefficient fixed to a constant function. And with this, we can learn independent relations in an iterative manner. Now, we also can provide some guarantees, like, for example, proving that the process of adding new independent relations will terminate. And also, we can extend this to a notion of strong independence and say something about the dimensionality of the learned data manifold. I won't go too much into detail about that, but you can look at the arXiv write-up. But I do want to mention another alternative definition of independence that we give via transversality. So this is coming a bit more from differential geometry, and this lets us look for relations that differ to first order, and it yields the same guarantees as what we obtained with the strong version of independence. So with the transversality, we would be looking for relations G1 through GK, and suppose we have found, relations G1 through GK minus 1 that are independent. For the GK's relation, we would want the gradients of this relation G with respect to the input sequences tau be linearly independent from all the previous ones. And then we would say that this relation GK is transfers to the previous relations G1 through GK. And for this, we can have guarantees on how that every time that we add a new relation, the dimensionality of the learned submanifold decreases. So formulating this problem as learning analytic relations lets us use neural network as function approximations. And so then these relations would cut out the latent data manifold that describe the subsequences that our actual dynamical system would take, and this lets us encode the kind of the regularities or the relations that occur in the actual latent space that we're interested in, like for example in general purpose simulator, right? So here is an algorithm. We would collect a set of trajectories, like for example, rollouts from RL actors that are currently, or RL learners that are currently training. Then we will learn the first relation G1 with the loss here. I won't go too much into the details of this loss, but basically it's saying that on manifold, meaning for the sequences that were actually sampled here, we would want this relation to hold. So we would want it to output some values close to 0, but we also want the gradients to be high because we don't want to learn just a constant 0 function or like a very simple trivial function with, let's say, all neural net weights being 0 or something like this. So with maximizing the gradient, we are able to learn a non-trivial relation that still holds on the data manifold, but perhaps does not hold off the data manifold, which is exactly what we want. Right, so with this we would learn our first relation, so that will output the values close to 0 for the sequences that actually come from our dynamical system. Then we will train the next relation with the same loss, except here, if we're aiming for transversality, we would also maximize the angle between these vectors v, and these vectors v, they represent the gradients with respect to the input of these relations with vjdk. And with this, we will be able to get that the next relation that we're learning is transverse to the previous one, and so on, continue learning relations G3, G4, and so on. Now, if we're interested in training with Syzygies, then we would start in the same way by training the G1 and then G2 independent from G1. But now we will generate off-manifold data, so either random sequences or sequences that are slightly perturbed to be off the manifold. And then we will train the syzygy, which would help us detect whether G1 and G2 are dependent. And the last layer of the syzygy would be encoded as a neural network as well, approximated by the neural network, but it will have a particular structure in the last layer where we would take the dot product of the outputs of the relations G1 through Gk and the last layer activations of the, next to last layer activations of the syzygy network. And then with that, we will try to find a relation, meaning feeding the off-manifold data as input and producing a 0 output. And if indeed we succeed in this training, that means that G1 and G2 are not independent. So we will freeze the syzygy, and then we will continue training G2 to push it away from the solution that made it possible to learn the syzygy. And eventually we will find the G2 that is independent from G1, because we would not be able to learn the syzygy that tells us that they are related. Okay, and then we will keep on going iteratively, now learning G3, G4, and so on, and then we will have this sequence of relations that capture the latent manifold of our sequences that are coming from the dynamical system. So here is just an illustration of how this modularity looks like on a three-dimensional example, so that it's easy to visualize. So there are no sequences here. It's just an analytic domain that consists of the on-manifold data coming from an intersection of the hyperboloid and the plane. So this is this hoop here, like a circle in 3D. And when we train with syzygies, we can see that first we capture some sort of this tilted bent plane, and then this bends away further and further. But when we take an intersection of all of these zero-level sets of the G relations, then we will get something that resembles the on-manifold data. When we train with transversality, we learn relations which are transverse to each other. So here in this case, G1 is a plane and G2 is a hollow cylinder, kind of intersecting this plane at almost the right angle. And if we continue learning here, insisting on trying to find more relations, then we're likely to find something like a plane and kind of like this tilted cylinder, but we'd also be able to find other relations, like, for example, these smoothed cones. Okay. We can also show that if we start by learning on an actual dynamical system, so here our training data consists of the short subsequences of the previous state, position and velocity of this block, and the next state, position and velocity of the block. This is how the unmanifold data is visualized with a phase space plot. So here we're plotting the position and velocity, and the arrows indicate the change in position and velocity on the next step. So this is just to visualize. This is a commonly used visualization tool for dynamical systems. When we learn the relations G1, G2, G3, we can show that not only do we capture the on-manifold data behavior, but we also can generalize beyond our training range. So here the training range is in this rectangle here, and you can see that the relation roughly captures the dynamics here, except for extrapolating this, because these indicate that the block kind of stops at the end of the incline. And of course, we are not able to extrapolate the behavior based on only seeing the range of sequences that happen at the beginning of the incline. Right, and likewise, we can show that we can capture notions like friction. So for example, here, these nearly horizontal lines show that we're basically stopping due to high friction, a high friction condition, and also nonlinear behavior when we have significant drag. So we can use this in order to improve the training of variational autoencoders and sequential variational autoencoders. Here, one version that we're going to show improvement on is a predictive sequential variational autoencoder, which takes in a history of observations and decodes or like up-constructs that history and the k next frames to predict. So with that, we will train the analytic manifold learning approach that I've described above to learn a set of relations that describe the domain with simple geometric shapes. So objects sliding down an incline, but like simple geometric shapes sliding down an incline. And then we will impose these relations on the latent state of this predictive VIE that is trained on this much richer domain. So now we're training from RGB images here with different textures and the objects that are actual coming from the meshes of the 3D scans of the real objects from the YCB data set. And with that, so this is the imposition here. We are using elbow of this predictive version of the VIE. So this is just a regular elbow here. And we are augmenting the loss with the imposing of the relations that we have just learned. And we also have a way of incorporating actions here. So action here is to push the objects to stay on in the middle of the incline. So with this, we can show that we get a better latent state alignment for the object position. So we can detect kind of the location of the object much quicker. And also we can show that imposing these relations helps us lower the distortion of the encoder map, which means that it better preserves the geometry of the low dimensional manifold. And this is something that people also look for when describing the quality of the embedding the map that we've learned. Okay, so this concludes that part. And now I will very briefly summarize the future directions. So here, let me speed this up. This is an example of how we would like to do deformable object manipulation, which is a whole different kind of level of complexity. And this is together with people from our lab. We set up this, they set up this kind of hardware environment where you can execute simple vision algorithms in order to pick up this shirt. But then here I'm going to be optimizing the parameter of the controller that actually puts the shirt over the head of the mannequin with Bayesian optimization. Now here it's just optimizing parameters of a restricted policy, no simulation-based kernel yet. But my long-term vision is that I will be able to capture the properties of the representations that are appropriate for these deformable objects in such a way that these representations would tell me something about their properties without the need to construct a particular simulation scenario like we usually do with the rigid objects, where in simulation we need to set up exactly the same scenario as what we will be using on hardware. So how can we achieve this? So first of all, we can enable topological data analysis on sequential data, currently working on these techniques where you can track some topological features through time. So this is our extension, and be able to say how you would like these topological features to appear more generally. We can also augment point clouds with contextual data, like for example, velocity of the gripper and robot arm, and improve the topological data analysis that tells us about the connected components and loops that appear in the scene, with being focused on the parts of the scene that matter. So with this, we can build a prior for a state sensitivity for common topological features and use this to infer state-dependent simulation fidelity to, for example, pick an optimal simulation step. This is what we would like to do. Another thing that we can do is we can warm start uncertainty estimation in model-based approaches, for example, because we would be acting based on the general topological features that are independent of the specifics of the objects, but they're dependent maybe on the relationship between parts of objects that are somehow salient because of their topology. And this could also ultimately, in the long run, help model-based learners to set, let's say, an informed planning horizon. And finally, I can envision that this direction could be extended beyond simulation and, for example, towards building approaches that convert large-scale models that have been trained on hardware data to priors that would help us learn new models and policies in a data-efficient way. So this would be kind of the former hardware to the new hardware scenario or updated hardware scenario situation. Okay, this concludes my talk. Thank you very much. I hope these were interesting topics. And here is the list of publications and preprints that I mentioned. There are a few Coral works and ICRA, JMLR publication with a lot more about bipedal locomotion and how to build kernels for that, and the more recent works that we have on analytic manifold learning and cloth manipulation. Thank you.